Well, we have page 7 and 8, and the activity on earthquakes, volcano, and plate boundary data. All those maps you looked at, the Smithsonian one where it had the kind of historical record of all these things happening. So, what I would like to go over here first is kind of what page 7 and 8 would have looked like before you did the extra stuff on the Google Doc. So you were just supposed to plot some of the points. You notice on this one, what did I do? Volcanoes were orange, earthquakes were brown. We had kind of clusters of them, especially on the western side of the Pacific. We had some along the western side of the North and South America. We had a few in the middle of the Atlantic Ocean. I kind of wish they had more kind of going right down the middle, but they don't. And then there were some in Europe. So there's some of these boundaries that you can get pretty decently, which was what the first part. First part on here asked you to just get your map of the earthquakes and volcanoes. Use the data that is already on your map plus the data that's on here. So I kind of did it in two steps. I drew the lines here that kind of made sense for maybe a plate boundary based on just the data that was on here. There was obviously going to be some type of plate boundary over on the west side of the Pacific. A lot of it, though, kind of left a lot of blank spots. Like, I have no idea how this is going to connect to over here. I can guess, since I know that there's a mid-Atlantic ridge, that this is going to go down the middle, but I don't really have a whole lot of data to help me out, which is why I found the website here from the Smithsonian. And what you notice when you look at here is you've got a lot of earthquakes. Some are pretty small, like we have smaller circles in the middle of the Atlantic, which means that we have small earthquakes there. But then when we get to some of these sides here where we already mapped earthquakes, we notice that a lot of them are pretty big, and there's a lot of them. Same thing with volcanoes. If I get rid of the earthquakes quick, you definitely notice that most of the earthquakes and most of the volcanoes that are erupting kind of happen on the Pacific Ocean here. Yeah, there's some other places, like on Iceland. There's a few down around Africa. There's a few that happen in the mid-ocean ridge. If we look at just earthquakes, you can definitely see that the brightest ones are, and largest ones. Brightest just kind of means that they happened recently, but if it stays bright like it does around the Pacific Ocean, that means that there's a lot of earthquakes. It doesn't really have much of a chance, like on the mid-ocean ridge, to fade out over time. That's all that that fading means, is that they happened a while ago. So that kind of comes back, and we'll talk about this more when we get into the plate boundaries here. The reason why there's a lot of earthquakes and the reason why there's a lot of volcanoes has to do with the type of plate boundary. They happen more frequently at one type than others. Okay. But otherwise, I just looked at this map and I obviously noticed that where my finger on the mouse here is tracing is a plate boundary. So I added it to my map. I noticed that there's a weak or faint boundary here that connects these. There's one that goes all the way around the bottom of the Pacific / Atlantic, just around Antarctica pretty much. There's one in the middle of the Atlantic. There's kind of some weird stuff going on here where there's probably some small plates. I noticed that there's this one right here in the Caribbean Sea. All right, so once I used all that information, this is kind of what I came up with on my map. I used a lot of that. There were some areas that were trickier because they were fainter, like in the Red Sea on between Saudi Arabia and Africa. There's very, very few earthquakes that happen there, so you might have missed that the first time around. The one that I missed for sure was there's kind of a boundary that goes right up here in the eastern part of Siberia / Russia. I technically missed the Caribbean plate the first time, but that's just because I kind of skipped over it. It's a little obvious that it's there. There is a connection between the Caribbean plate and the mid-Atlantic ridge, which is a little tricky to find. Like there's no earthquakes really that are happening there right now, so you don't even really see it. All right, so go back here. Apparently I missed going back over on this side on this particular picture. And that was where I had missed the Caribbean plate. I hadn't really connected these that well yet, but when we get to the part of the worksheet that says, now compare your drawing to maps in this website of plate boundaries. So we go to that website, which is this one, and the best picture for just doing the plate boundaries is the one that literally labels them for you. So we notice that there's a Philippine plate that kind of had that weird split in the volcanoes and earthquakes over there. There's a boundary that kind of goes up through Siberia, which I added. I added my Caribbean plate. I finished my connection over there, which I just kind of forgot about on the first time around. And it did help me draw some of the boundaries in the Indian plate and Arabian plate and Eurasian plate, because some of those are a little blurry or they weren't that bright of a boundary on that activity or map. So that took me to this next one, the next step in my map, where I finally drew in some of those ones that I was missing. I added some lines, I completed my Indian plate, and then I labeled 5 of them. So you just get those names from that picture we were just looking at. The Pacific plate, the Nazca plate, Caribbean, North American, South American, African, Arabian, Eurasian, Indian plate. I think this was like the Cocos or something like that. I forget what that one up there is. Oh no, got them wrong. That's the Cocos. This is the Scotia. The other one that I added in later, that's kind of a weird one off the coast of Oregon and British Columbia, is the Juan de Fuca. It does some weird things out there, and I just kind of added it once I did the plate boundaries and colored them. So that was the next step, was actually labeling some of these different colors. So divergent boundaries, label blue, convergent red, transform yellow. So the maps that helped me the most with that was the very last one, and this one you could get it from, but it's a little bit more of a cluttered map and it's harder to see some of the things on it. This one to me had it more color coded already, but the divergent boundaries were split up into what I talked about on the video yesterday, is when you have these mid-ocean ridges that are spreading apart, since our globe isn't flat, it's a sphere, there's some faults or transform boundaries that have to happen. So it's not just one giant ridge, there's one line of things all the way up the Earth. There's one part that splits apart, and since it's a sphere, you're going to have a part next to that that goes just side to side, and then you have another one over there, and it splits apart. And you have these kind of divergent boundaries with a transform or a fault in between. So it kind of makes this zigzag up the Earth. But that's not the point that I wanted. I'm just calling this, lumping it all together, calling it a divergent boundary. That's overall what happens there. The ocean gets bigger. So this is the map I used to help me do the divergent boundaries, because all divergent boundaries, for the most part, are ocean ridges. So wherever I saw an ocean ridge, I colored it whatever color it asked me to, which was what? Blue? Okay. So I used that map there to do all of my ridges blue, and that's where I brought in that little tiny plate off the west coast, the northwest, the Juan de Fuca, and I put a little tiny ring there that was blue. But on the other side of it, it's a convergent boundary, so it was red. Okay, so this is kind of the final map here that I had everything labeled on. Some of the questions asked you to label like the mid-ocean ridge or mid-Atlantic ridge, which you could have labeled any part of this. And then I added my arrows to show what way the plates are moving at an ocean ridge. So they're always moving apart at a divergent boundary. So wherever you had a blue, you could have drawn those arrows as long as they were like this one pointing up, that one pointing down. I did convergent boundaries, red, so almost all the way around the Pacific plates, I have convergent boundaries. So that's where the plates come together, which I showed right up here by Canada. They're pointing towards each other. And then there's by far less transform boundaries, at least the longer ones. So I've got one in California, I've got some along the Caribbean plate, there was some along this African and Eurasian plate, around the, I forget what that one was called, whatever that plate was down there, and then this little section there. So definitely have a lot of divergent boundaries, a lot of convergent boundaries, and transforms are kind of the least common overall. I labeled my San Andreas Fault, which is in California. That's on a transform boundary. I picked the Marianas Trench because I've heard of it the most. It is the deepest part on the Earth, deepest part of the ocean on the Earth. I think it's like 7 miles or something deep underneath the surface. But any trench, if you picked any of these convergent boundaries that are right on next to the ocean and a continent, you're going to have a trench there. So you could have labeled any of those. You wouldn't have a trench here because it's not in the ocean. So you couldn't have labeled the Himalayas as a trench because it's obviously trenches happen in the ocean. Okay, so that's what page 8 would look like at the end there. You'd have 5 plates labeled, you'd have all of your boundaries colored, you would have labeled a trench, the San Andreas Fault, the Mid-Atlantic Ridge. Okay, that brings us to the rest of the questions on this Google Doc. So it asked after you labeled the Mid-Atlantic Ridge, it asked what country in the world where you could walk through an ocean ridge on the surface. And I had talked about that in class before we left for this e-learning break. And that was obviously Iceland. You could have Googled it, but Iceland has a volcanic hotspot under it, so there's kind of extra magma that creates more volcanic eruptions, which means that Iceland gets bigger and it actually sticks up above the ocean. Okay, then just describing what a trench is. So a trench is a very deep part of the ocean. It always happens where oceanic crust hits, usually like thicker continental crust. The oceanic crust is deeper and denser, so it's the one that slides under, and therefore you have this deep part of the ocean right where those two meet, which is called the trench. So what happens where a subducting or plate that slides under hits that convergent boundary and creates the trench. Okay. The Himalayas also happen at convergent boundaries, or just mountain building in general happens where two plates meet each other. So instead of having a skinny ocean plate here where the Indian plate meets the Eurasian, you have two continental crusts hitting each other, which isn't going to slide under like an oceanic plate would because they're roughly the same density. So instead, they buckle and they smush together and they form thicker parts of the crust, and those thicker parts are the mountains. Okay. So then, on what type of plate boundary do the highest number and largest number of volcanic eruptions happen at? So I kind of showed us that before. If you just look in general where most of the volcanoes are, they're definitely happening all along the Pacific plate here. And those happen to be, if we look at our map, all where those volcanoes are happening are convergent boundaries, particularly where one plate slides under the other, meaning we have a trench forming there. You notice that there's should be no volcanoes where the Himalayan mountains are. Yep, no volcanoes at all. So when two continental plates hit each other, it doesn't make any volcanoes because there isn't that plate that's sliding under and melting and making volcanoes on the plate above it. So we have to have particularly oceanic crust going under some other type of plate. Doesn't matter if it's another oceanic plate or a continental plate. It just has to slide under, and that's where we'll form most of our volcanoes. There are a few that happen like on the Mid-Atlantic Ridge, which is obvious. It's just they're not as frequent, they're not as common, or they're under the ocean, so we don't really know they happen. Could be another reason too. Okay. So, highest number of volcanoes on convergent plate boundaries. Not just any convergent plate boundary, it has to be where oceanic crust slides under another or subducts under another. Okay, then that sets us up for the Ring of Fire. So a Ring of Fire has to do with volcanoes, magma, fire, that kind of stuff. So we notice that there's a ton of volcanoes around the Pacific Ocean. It almost completely circles it. So that's why they called it a Ring of Fire. There's a lot of volcanoes around the Pacific Ocean, and it almost circles around the whole entire thing. And then there are tall mountains along the west coast of North and South America. So using that information, why are they there? So that's also a convergent plate boundary where plates are crashing into each other, which just kind of creates that squishing and mashing of the continental crust, which makes mountains, first of all, even though it's not two continental plates hitting each other, that force still buckles the plates and creates mountains. We also have that volcanic part adding to it as well. So if there's magma coming up and adding rock to the surface of the earth, that's obviously going to build mountains too. Okay. And then oceans, so it asked us about the Pacific and the Atlantic. What we notice is that right down the middle of the Pacific or the Atlantic, we have that divergent boundary, which means that the seafloor is spreading, getting bigger. We're adding new crust, we're making new crust, so the Atlantic Ocean is getting bigger over time. Where the Pacific has mostly convergent boundaries around it, which means that there's a plate sliding under another plate, and that's essentially recycling or destroying the oceanic crust, and they're keeping crashing into each other, and they are kind of destroying that crust and getting smaller. So Atlantic Ocean gets bigger because of the divergent boundary. Pacific Ocean is getting smaller because of all the convergence. Okay. So last question here was using your map, what type of boundary is a fault? So after you labeled the San Andreas Fault, you should have noticed that it happened on a transform boundary. So whenever you have a fault happening, you have rocks sliding past each other, and that is a transform boundary or a fault. Okay. Then otherwise, I think your assignment for today is to work on pages 9 through 13. Two of them have to do with just drawing the different plate boundaries. One of them has to do with graphing or plotting earthquakes by depth and distance from the edge of a plate boundary. then the last one has to do with convection cells and how those help move the crust itself and what they are. Otherwise, I'll post another video about that tomorrow for the answer key there. And if you have any questions, feel free to reach out to me.